Hello.
Hello.
Hi. Okay. So today I want to cover two things. First, the proof of the uh, Euler's phi function is multiplicative, right?
Yeah.
And then Chinese remainder theorem. So that will be the major part of the class. Chinese remainder theorem. But before that, we'll do this proof. So we want to prove this whenever M and N have GCD 1. When M and N are co-prime, we want to prove that the phi function is multiplicative. So, so let's do this. So the theorem says, suppose M and N are relatively prime, then what we have to show is that among the integers, we have to find out phi of mn, right? So phi of mn means all the numbers from 1 to mn which are co-prime to mn, right?
Yeah.
Among the integers from 1, 2, 3 till mn minus 1 comma mn, how many? We have to show that there are exactly phi m multiplied by phi n integers that are relatively prime to mn, that are co-prime to mn, correct?
Yeah.
So that is what we have to prove, and we'll do this in a nice way, uh, sort of like a matrix diagram we'll draw. So I will make a matrix here, and it will list out all of these numbers. So let's see how we are making this. 1, 2, 3. Let's say here there is h, and here there is goes on till m, right? So basically m rows, right?
Yeah.
And columns will be, this number is 1 into m plus 1, and this is 2 into m plus 1, and so on, so on. There is one k into m plus 1, and the last one is n minus 1 into m plus 1. So if you see carefully, this is 1, 2, 3, n minus 1 here, right? And
Yeah.
1 here. So total number of columns are n, right? N columns, right? So here, what we do is, it is 1 into
And
m plus 2. And this is 2 into m plus 2. And this is k into m plus 2. And this is n minus 1 into m plus 2. Okay.
yeah.
So whatever number is 2 here, that is added plus 2 plus 2 plus 2. And you start 1 into m plus 1, 2 into m plus 1, go till n minus 1 into m plus 1. So here it will be 1 into m plus 3, 2m plus 3, km plus 3, n minus 1 m plus 3, right?
Yeah.
I'll just fill this up. This will be 1 into m plus h, 2 into m plus h, k into m plus h, n minus 1 into m plus h. And last one is 1 into m plus m, 2 into m plus m, k into m plus m, and n minus 1 into m plus m. And notice that this is equal to mn. Right? N minus 1 into m plus m is mn, right?
Yeah.
You
Yeah.
start from 1 and you are ending up at mn, right?
Yeah.
And m rows, n columns. So we have made this table of numbers. Now think about it. If the first element, the first number in a row is H, and if BCD of H and M is not equal to 1, right?
Mhm.
That means HM have a common divisor, right?
Yeah.
Common divisor. Let's say D, right?
Yeah.
So if that happens, H and M have a common divisor, then
Oh,
you can say that D will divide all of these numbers, right?
this is like the Euclidean algorithm.
We will basically cancel off numbers which are not coprime. Okay. So this is like there is one uh, sieve method, no, Eratosthenes' sieve method of finding prime numbers, right?
Well, what's this?
Basically, if you have to find out numbers that are prime, then you can list down all the numbers and then cancel off stuff that is divisible by 2, and then cancel off stuff that is divisible by 3, right?
Yeah.
And then very quickly you will get numbers that are going to be prime, right?
Yeah.
So we'll see how it is. You will understand this very simple proof. So for now, just try to think. What we will say here is if the first number of a row is H and GCD H and M is not 1, then H and M have a common divisor D, and therefore all numbers in the row are divisible by D, right?
Yeah.
Are divisible by D, correct?
Yeah.
So, there is no number in that row that is relatively prime to M, right?
Yeah.
Relatively prime to M. And if you are not relatively prime to M, that means you are not relatively prime to Mn, right?
Yeah.
Correct.
Yeah.
So basically now we are saying that if GCD of H and M is not equal to 1, right?
Yeah.
Then that entire row is cancelled, right?
Yeah.
Because that entire row will have all the numbers will be divisible by H and M, divisor of D, and therefore it will not be relatively prime to M, right?
Yeah.
Okay, so that means that we have to select, which rows? Rows where
Or the H and
M are co-prime,
yeah.
right? Only those rows where H and M are co-prime, right?
Yeah.
Only those rows can have any number that is relatively prime to Mn, right?
Yeah.
So how many rows are there? There are M rows. And how many numbers are there from 1 to M which are co-prime to M?
That's 5M.
M. 5M rows are present, are such, right?
Yeah.
So we already know that out of these rows, only 5M rows are useful, correct?
Yeah.
Okay. Now we'll focus on the columns, right?
Yeah.
So now we will say that, let's say we are in one of those 5M rows, right? I will just rub off this part here now, okay? So I am going to say in each of these 5M rows, I have to prove that there are 5N numbers that are co-prime to Mn, right?
Well,
We
five.
already know number of rows, right?
Yeah.
We have to prove that in each row there are 5N so that we get 5M into 5N total,
Yeah.
right? So
Yeah.
that is what we want to prove. So now let's consider one row where HM is 1, right?
Yeah.
So HM GCD is 1, so that is a row which is possible, correct?
Yeah.
So first first you observe that in, let's say this is one of those rows. This is one row like that, correct? So
Yeah.
first see that there are n numbers in the row, n numbers in the row, and each number is distinct modulo n. How can we say that? Each
Oh,
number is distinct modulo n
because
because
we can minus h and it's 0 m 2 m and until m minus 1 m and
uh,
m and n are co-prime.
because already we know m and n are co-prime, right?
Yeah.
And uh, if you do congruent modulo n, right?
Yeah.
Then first of all, there are n of these, and we can actually just prove it by saying, let's take two different elements here. Let's say jm plus h and km plus h, right?
Yeah.
If they are having if they are same congruent, or they are congruent modulo n, then we have jm plus h is congruent to km plus h mod n, and that means h can be subtracted, and that means jm minus km is congruent to 0 mod n, right?
Yeah.
And that means n divides j minus k into m, right?
Yeah.
Now, since n does not divide m, so this implies n must divide j minus k, right?
Yeah.
But j and k are lesser than n, right? It goes up to only n minus 1, right?
Yeah.
So this is not possible, right?
Yeah.
Correct.
Yeah.
So that means these two can never be congruent modulo n, right?
Yeah.
So these two are to have to be distinct modulo n. And how many of them are there? There are n of them, right?
Yeah.
So that means that we are basically saying that this entire row is composed of these 0, 1, 2 till n minus 1 residues, right?
Yeah.
They might not be in the same order, but since they cannot be congruent to each other and there are n of them, they must be some of these, right?
Yeah.
Now, if all of these are distinct congruent modulo n, how many of the numbers here are co-prime to n, right?
Of that's phi n.
Phi n, right? Phi
Yeah.
n are co-prime to n then, right?
Yeah. Also, like we select phi n from each row.
And such rows over phi m,
Yeah.
right? So total number of such numbers will be phi m into phi n, right? Which
Yeah.
is your phi of mn now. Okay.
Okay.
So once we have this proof, what we know now is any number that you give me, I will be able to find the phi totient function for that. Number of numbers that are co-prime to it less than it, right? So
Yeah.
if I say 24, I will say this is equal to 2 cube into 3 power 1, right?
Yeah.
And 2 cube and 3 power 1 are co-prime to each other. So it will be phi of 2 cube into phi of 3 power 1, right?
Yeah.
And this is what? Phi of 2 cube.
Phi of 2 cube. Hey, wait, what's the formula? I
And
forgot.
there was a formula p power k minus p power k minus 1, right?
Yeah.
2 power 3 minus 2 power square.
Yeah.
And this is 3 power 1 minus 3 power 0, right?
Yeah.
So this becomes 8 minus 4, 4
4 times.
multiplied by 3 minus 1, 2. So total is 8, right? And
Yeah.
you can now basically, since every number is guaranteed to have a unique prime factorization, you can always find the phi for anything, right?
Yeah.
Because of this multiplicative property,
Yeah.
correct?
Yeah.
Okay. Okay, so next thing that we'll start doing is Chinese remainder theorem. This is a very useful concept and it is applied in many problems. Maybe not directly, they might not say that it is this, but basically you want to be able to solve congruences. So solve equations where there are x and stuff and congruences, right?
Yeah.
So the theorem says this. Suppose n1, n2 till nk belong to natural numbers, and each of these are pairwise relatively prime. Relatively prime. Basically, that means that GCD of Ni, comma Nj is equal to 1 for all I not equal to j, right?
Yeah.
All of these numbers are pairwise relatively prime. Similarly, there are another set of numbers b1, b2 till bk, which are also belonging to n, right?
Yeah.
Actually, this can be integer z. Okay. Then we will have a system of linear congruences. The system of basically it's a system of equations, system of linear congruences rather than equations, which is like looking like this. X is equal to b1 mod ni n1. X is equal to b2 mod n2, and so on till x is equal to bk mod nk, right? Now, suppose this system of congruences is given to you and you are supposed to find x, right?
Yeah.
So the theorem says that this system of linear congruences has a unique solution modulo n1, n2, n3 till nk, this product. So this is the statement of the theorem, that this system of congruences has a unique solution modulo product of all of these n1s, right? And the condition for the theorem was what? Each of these n1s were relatively prime, right?
Yeah.
And the equation was set up like this. So what we will do here is we will try to construct a solution to this congruence. Okay. And by constructing it, we'll prove the statement. We'll prove that the system of linear congruences has a unique solution this, right? So just write this down. I hope you have written this because I'll go to the next screen and say the next thing.
Yeah.
Just write the statement of the theorem in your notebook and then we'll continue.
Okay. Okay. Finished.
Okay, fine. So our congruences were like this. X is congruent to B1 mod N1. X is congruent to B2 mod N2, and so on till X is congruent to BK mod NK. And we want to solve this system. So what we'll say is let us look at the number capital N is equal to N1 into N2 multiplied by Nk, right?
Yeah.
And and let capital N subscript I, Ni, is equal to capital N by small ni. So what is small ni? Are these n1, n2, and more, right? So
Yeah.
basically, ni is what? Ni is this product only except n1 has been removed, right?
Yeah.
Or n, basically I will also go from 1 to k, right? There will be n1 which will look like this, n2, n3 till nk. N2 will look like this, N1, N3, N4 till Nk, and so on, right?
Yeah.
Nk will look like N1, N2 till Nk minus 1, right?
Yeah.
So we are constructing two numbers. One number is this capital N and all the Ni's like this, right?
Yeah.
Now, the first step is this claim that you can show that GCD of capital Ni with small ni is equal to 1. Can you think about this?
Yeah. Because like
Huh.
for each in J that is not I,
Hmm.
and a small ni and small ng, GCD of small ni and small nj is
Was
1.
1,
So
right?
we
That's
multiply
right.
everything.
That was earlier said already that each of these small ni's are co-prime, right?
Yeah.
And this capital Ni does not have the Ni, right?
Yeah.
It has all the other n's, right?
Yeah.
So obviously it will be co-prime with this because each small ni is co-prime with everything that is inside this, right?
Yeah.
So we know that GCD of ni comma small ni is 1. That means this implies that ni has an inverse modulo ni, small ni. Why? Because if this is 1, I can write ni x plus small ni y is equal to 1, right?
Yeah.
And then if I take modulo ni here, I can say nix is congruent to 1 mod ni, right?
Yeah.
Because this is 0 mod ni, right?
Yeah.
So therefore, x is the inverse, right?
Yeah.
X is the inverse of ni mod small ni, right?
Yeah.
Correct. So now we know that there is an x, right? Such an x. So let's call that xi, actually, xi, right?
Yeah.
So there exists xi such that nixi is equal congruent to 1 mod ni, right?
Yeah.
Because the GCD of this is 1, therefore the inverse exists, right?
Yeah.
So now, and for each such capital Ni, like N1, N2, N3, there will be an inverse X1, X2, X3, right?
Yeah.
For each, this I can be anything from 1 to K, right?
Yeah.
So let's now look at this number. Capital X is equal to N1, X1, B1 plus N2, X2, B2 plus N3, X3, B3 and so on till nk, xk, dk, right?
Yeah.
One thing that I did not mention here was any nixi is congruent to 0 mod nj, right?
Yeah.
Because ni itself has nj term in it, right?
Yeah.
Makes sense, no? Ni is a multiple of nj.
Yeah. 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 I know.
Nixi is only going to be 1 mod the same ni, same I, right?
Yeah.
Okay. So now if you look at this number, right?
Yeah.
Let's look at it mod ni, x mod ni. So what will this be? If you don't, this is 0, right?
Yeah.
Suppose 1 does not match the I.
Yeah.
So n1 x1 will be 0 mod ni, right?
Yeah.
Plus 0 plus there is one term which will be ni xi bi, right?
Yeah. So that's bi.
1 bi, right? Mod ni, right?
Yeah.
Plus everything else is 0, right?
Yeah.
So what we are getting is x is congruent to bi mod ni, right?
Yeah.
And the same thing is true for I goes from 1 to k right now. Because I did mod ni, I could have done mod n1, mod n2, mod n3. I'll keep getting results like this, right?
Yeah.
So what we have shown here is, look, this was the original equation, right?
Yeah.
This was the original congruence, and we have actually constructed the number that will solve those congruences, right?
Yeah.
Correct. So we started off by taking product of all of those n1, n2, nk, and constructed ni to be n by ni. And we, because GCD of ni small ni is 1, therefore inverse of ni exists, and those inverses are called ni xi, right?
Yeah.
So you find all the inverses and construct the new number n1 x1 b1. b1 is from the remainders here.
Yeah.
n2 x2 b2, n3 x3 b3, and so on. And once you get that, that is your solution. The sum of those is your solution, because that clearly satisfies x is equal to bi mod ni for I goes from 1 to k, right?
Yeah.
So we have not yet proved the other part of the question, which says unique solution. So uniqueness, right? So for uniqueness, we can say that let x and y both be solutions to the initial system of equation congruences, right?
Yeah.
So that means x is equal to bi mod ni and y is equal to bi mod ni for all 1 is less than I is less than k, right? There will be k equations in each, right?
Yeah.
Then we can immediately say x minus y is congruent to 0 mod ni, right?
Yeah.
And we can say that basically ni divides x minus y for all 1 is less than I is less than equal to k, right?
Yeah. So also the capital N divides x minus y.
So capital N, correct, correct. So basically x minus I is divisible by ni, and since ni and j alone are all co-prime, x minus I is divisible by product of them, right?
Yeah.
By
And
capital N.
since we're taking modulo, then x is congruent to y.
So x is congruent to y modulo capital N, and capital N was n1, n2 till nk, right?
Yeah.
So the uniqueness part of the theorem said that it is congruent, unique solution. There is a unique solution congruent modulo n1, n2, nk, right?
Yeah.
So that is what this part is saying. We have proved that if there are two solutions, they will always be congruent to each other, modulo n1, n2, nk, right?
Yeah.
So let's look at a couple of questions here. Just to reinforce what we have learned. So question 1 is this: you have to solve the system x is congruent to 1 mod 3, x is congruent to 2 mod 4, and x is congruent to 4 mod 5. This is question 1, and question 2, you have to find x, and question 2 is this one. Uh, x is congruent to 2 mod 4. X is congruent to 1 mod 5. X is congruent to 3 mod 9. And x is congruent to 7 mod 13. So in both the cases, we want to find the relevant x.
Okay.
So just use the theorem, the proof that we did, the same method to try to construct the solution.
Okay. The first one is 34, right?
Correct. First one is 34. So you get N60, N1 20, N2 15, N3 12. And then you have to find X1, X2, and X3, right?
Yeah.
So N1, X1, N1, X1 mod 3, right?
Yeah.
N1, X1 is equal to 1 mod 3. And X1 now will come out to be 2, right? 20x1 is equal to 1 mod 3.
Yeah.
And that will be
40.
2. X1 will be 2. One way to do it faster is you can reduce 20x1. Instead of that, you can say 20 is 2 mod 3, right?
Yeah. So
So you can say 2x1 is equal to 1 mod 3. And
yeah.
2 into 2 will be 4 is 1 mod 3, right?
Yeah.
X1 will come out to be 2, and similarly, X2 will come out to be 3, and X3 will come out to be 3, right?
Yeah.
And when you construct the number capital X, it will be N1, X1, B1. B1, B2, B3 were 1, 2, and 4, right?
Yeah.
So when you do N1, X1, B1 plus N2, X2, B2 plus N3, X3, B3, it will come out to be 214, right?
Yeah.
And mod of 60 you have to say, because that was mod n. So that is 34 mod 60, right?
Yeah.
So that is this one. The second one is slightly longer. It's just the same thing though.
Yeah.
Maybe you can do it at home later. Like I will tell you the answer. Second one answer should be x is equal to, you can do it later. Okay. X will be 1866 mod 2340. That is your solution. So it's the same method, just try it later. Right
Okay.
now, we will do this one. Question is this: solve 4x is congruent to 5 mod 9 and 2x is congruent to 6 mod 20. Now, this is slightly different because notice that 2, 6, and 20, right?
Yeah.
So, and in Chinese remainder theorem, we didn't have 4 and all, right?
Yeah.
We
So
didn't have these numbers there.
can I time the second equation by 2, like 4x is congruent to 12?
What are you doing here?
Yeah.
Uh, you can anyway, multiplication is never a problem, right?
Yeah.
Multiplication of a congruence is never a problem, but it would be nicer if you just divide, right?
But
So
like, I cannot divide the first one.
first one you can't divide. Oh, you are trying to make it 4x here.
Yeah, then I make it the same thing. So I call it y. That's all for y.
Correct. That is a good way to do it also. What I would have done is make everything x. So how to do that? So I will we can discuss that as well. You can try your solution also. Just you can try your method. Just try it for 3-4 minutes, and if you get the answer, then we'll discuss my approach as well. Okay. Your method is correct. You can multiply by 2, 4 and call it y, and then solve for y, and later think about what it is. Right?
Yeah.
Tell me when you have gotten something for y.
I made some calculation mistake.
Okay. It will come, your y should come mod 180, right?
Oh, yeah.
Right.
Hey, wait up. It's correct. Is it correct? I'm not sure.
What is coming for y?
My calculation was completely wrong because like I found the wrong
Oh,
x. I found the wrong like
okay.
the first stage. So I need to do the whole thing again.
Okay.
Y is 32.
Y is 32.
Yeah, then divide by 4 is 8, right?
Capital X should be, you got x1 is 5 and x2 is 9, right?
Oh yeah.
So it will be n1 20 into 5 into 5 plus 9 into 9 into 12, right?
Yeah.
So 500 plus
972.
81 into 12, right? 972, correct. So you should get 1472 mod
Yeah.
180.
Then I minus 1440 is 32.
1440, okay, is 32. So you're getting y is 32 mod 180, right?
Yeah. Okay.
Okay. Then y is actually 4x, right?
Yeah.
So 4x is 32 mod 180 you're getting, correct?
Can I divide by 4?
So now think about it. Uh, when you we discussed this property earlier, like when you have AD is equal to is congruent to BD mod C, right?
Yeah.
And you want to divide by D, right?
So I have to divide C by D also.
It is mod C by uh, I think GCD of D and C, right?
Yeah.
Right. This was the property that we saw earlier, no?
Oh yeah.
Correct. So I want to divide by 4 here, right?
So I have to divide by 4 by
Huh.
for 180.
So 8 mod, it should come 180 by 4, right?
Divide.
So that will be 45, correct?
Yeah.
8 mod 45 we are getting,
Yeah.
right? So 8 mod 45. So that is like 53 mod 90, right? What is 8 mod 45? If you look at this,
We have several like
there are
possibilities.
multiple possibilities. Options are 8, 45, no, 8, 53, and then
98.
98, and then 143, right?
Yeah.
And then uh, plus 45, 135 plus 45, 180. So 188, that is not going to be there. So till here, these are the possibilities that we are getting, right?
Yeah.
Now, the actual answer is 53 and 143 mod 180. Okay. So I'm just thinking why 8 and 98 are not correct. Uh, This is correct almost. Like you're getting more solutions, but two of the solutions have to be rejected. So can we think of a reason why 8 and 98 are not correct? And 53 and 143 mod 180 is correct. If you think of 8, like let's put the number 8 in the original congruence, right? It doesn't fit, I think. 32 is fitting. 8, 16 is 6 mod 20. No, this is not fitting, no?
Yeah,
Right?
but
And
it is for mod 10.
what?
I mean, 16 is congruent to 6 mod 10. So why
That's
is it?
fine, but we have to do mod 20, no? 16 is 16 mod 20.
So like, yeah, I also don't know why.
No, sometimes it happens, no? When you solve equations, if you change the variable, sometimes extra solutions can come, right?
Yeah,
Like in a quadratic equation, if you change the variable, and in a difficult equation, if you have made a substitution, you can either get extra roots or you can lose some roots if you're not careful, right?
so I
So,
have to do
so,
try and error.
so you can check at the end which solutions are fitting, right?
Yeah,
You will see that 53 fits both. 53 into 4 is 212 and 180 and and 27 high. It is 5 mod 9, right?
yeah,
And 106 is 6 mod 20, right?
yeah,
98 into 2, 196 is not 6 mod 20, right?
yeah,
98 does not fit, right?
yeah,
143 into 2, 286 is 6 mod 20. 143 into 4 is 572 and 540 and 32. Again, it is correct. This also fits both, right?
yeah,
So from this method that you have done, we are getting the solutions. We are getting extra solutions, 4 solutions we are getting. If we look at mod 180, right?
yeah,
And out of which 2 are correct, 2 have to be ignored, right?
yeah,
The other way that I was going to do was this. If 4x is 5 mod 9 and 2x is 6 mod 20, right? So first of all, I will change this, and I know that I want to remove 2 and all, and I want to remove 4 also from here. We'll do that in a bit. But if I want to remove 2 here, divide by 2, I'll do x is congruent to 3 mod 10, right?
yeah,
Because 20 by GCD of 2 and 20, which is 2.
yeah,
So x is congruent to 3 mod 10 is one equation. And this I have to think about what to do, right? Because here these are relatively prime, 4 and 9, right?
yeah,
And I cannot divide by 4 and all. That doesn't make sense. But what I can do is multiply both sides of a congruence by something, right? Equal, right?
yeah,
If I multiply both sides of a congruence, okay, first thing to note is since GCD of 4 and 9 is equal to 1, therefore there is an inverse of 4 modulo 9, right?
yeah,
We know this. As long as two numbers are co-prime, there will be an inverse with respect to each other, right?
yeah,
Right. What is this inverse? X should be uh, 2, no, not 2. 6 is 24, 7 is 28. 7, right?
yeah,
Correct.
yeah,
So x is 7 is the inverse of 4, right? So
7, yeah, yeah, yeah,
modulo 9, 7 is the inverse of 4, right?
yeah.
So what I will do is I'll multiply both sides by 7, right? Correct.
So it's like 28x is congruent to 35.
20x is 35 mod 9, right?
Yeah.
And we know 28 is 1 mod 9, right?
28 or
28 is 1 mod 9, no?
yeah.
So that just removes this, right? You understand what I'm saying?
Yeah. Like I thought the easier way,
Huh.
you just add 27 to 5.
Uh-huh.
So that's 4x is congruent to 32 and you can divide.
No, we can't divide because it's still mod 9. No?
Yeah, I know, but you can like add 27 because 27 is congruent to 0 mod 9.
That's correct. But you will get 4x is congruent to 32 mod 9, right?
Yeah,
Then how will you divide by 4?
because like 4, the GCD of 4 and 9 is 1, so like we can divide.
Here also, correct. You are correct. You'll get x is equal to 8 mod 9 here also, right?
Yeah.
And here also you're getting x is 8 mod 9, right?
Yeah,
So basically, what I was doing was just multiply by the inverse. So 28 is just 1. So it becomes x is 35 mod 9. And you get x is equal to 8 mod 9 is my second equation, right?
yeah,
Once you have this, this is in the form that you can do Chinese remainder theorem, right?
yeah.
So quickly we will do it. N1, N2, N capital N is 90, N1 is 9, N2 is 10, right?
Yeah,
Capital N is 90, N1 is 9, N2 is 10. And let's find X1. N1 X1 is congruent to 1 mod 10, right? So 9 X1 is 1 mod 10.
x1 is 9,
So X1 is 9 and
x2 1.
10 X2 is congruent to 1 mod 9. 1 mod, wait, here it should have been 9, no?
Oh yeah,
Right, I'm making a mistake. This is 9, right? N1 X1 is congruent to X1 should be 1, right?
wait,
Right, no, it is 9, no, first. Correct.
no, but like n1 is 9,
N1 is 9, no? So first equation is N1 X1 is congruent to 1 mod 9, right?
but 9 times something is
Oh,
always equal to 0, right?
wait 1 second. My
So like
my equations are these two, right?
yeah,
So these two are my equations. So I have to label everything properly. Small n1 is 10, let's say, and small n2 is 9, right?
yeah,
Then that's why your capital N1 was 9, because 90 by 10, right?
yeah,
So N1 X1 is congruent to, we have to do 1 mod 10, right?
yeah,
And this is 9x1 is congruent to 1 mod 10. Now it is correct. X1 is 9, right?
yeah,
And N2 X2 is 10 X2 is congruent to 1 mod 9, right?
yeah,
So this time it will be
x1,
X2 is just 1, right?
yeah,
Correct. So capital X is N1 X1, 9 into 9 into B1. B1 is 3 plus N2 X2, 10 into 1 into B2 is 8, right?
yeah.
So this becomes 243 plus 80, which is 323, right? And
minus,
mod 90 we have, right?
minus 270.
So x is equal to 53 mod 90,
Yeah.
right? So if you think of mod 180, the numbers will be 53 and 53 plus 90, right?
Yeah.
Which is 143. So we are getting the two solutions that we got in the previous solution also, right?
Yeah.
53 and 143, but this time we are not getting any extras,
Yeah.
right?
Yeah.
So in general, you just have to learn how to apply Chinese remainder theorem. Sometimes the problems may not be direct, like this one was not direct. You have to do some stuff before, right?
Yeah.
Okay. Then now what we'll look at is a slight generalization of CRT. So another theorem we'll look at. So Chinese remainder theorem can be stated like this. Suppose GCD of M and N is 1, then the system X is congruent to A mod M and X is congruent to B mod N, has a unique solution modulo Mn. In the previous case, we had done in a more general case. I'm just writing it in short for two equation situation, right?
Yeah.
Now, the generalization that we want to look at is this theorem. This theorem states that the system X is congruent to A mod M and X is congruent to A mod N or B mod N congruent to B mod N has a solution if and only if. See, right now in this question, in this theorem, we have not yet stated that GCD Mn is 1, right?
Yeah.
M and N can be anything right now. It doesn't have to be coprime, right?
Yeah.
This has a solution if and only if GCD M and N divide A minus B. That is one statement. And the second part of the statement is the solution, if it exists, is unique modulo LCM of A and B. Okay. Okay, so let's look at this one. First, think about it. If GCD M and N, I feel like I have made some mistakes somewhere. A and B, why am I writing? It is M and N, I think. This is M and N. Think about it. If GCD of M and N is 1, right?
So yeah, this is very obvious. Just
Then it becomes the Chinese remainder theorem, right?
yeah.
Because LCM is Mn then.
Yeah.
Right? So we have to prove this because right now it is not obvious why this has to be true, right? So first we have to understand when is a system of congruences where M and N are not necessarily co-prime going to have a solution. And apparently this is the condition. The condition is this, right?
This is the Bezos lemma, right?
It is similar. So from there only you will get the solution. So just write this once. We will do the proof now after this. If you have written this, we can go to the proof.
Let me write it down.
Yeah.
Okay.
Right. Okay. So we'll prove both sides of the statement. This is an if and only if statement. So first side that we'll prove is this, that suppose X is a solution to X is congruent to A mod M and X is congruent to B mod N. Then we want to show that GCD of M and N will divide A and B, right?
Yeah.
Correct. So that is one side. So here what we know is this implies if X is a solution of this implies M divides X minus A and N divides X minus B, right?
Hmm.
Therefore, X minus A can be written as M times K1 and X minus B can be written as N times K2, right? K1 and K2 are integers,
Yeah.
right? And you can say X minus B minus X minus A will be equal to A minus B and will be equal to NK2 minus MK1, right?
Yeah. Oh, so
Correct. So this side is a linear combination of M and N.
like it is divisible by
GCD of M and N.
yeah.
It is divisible by GCD M and N. Therefore, we can say that GCD M and N divides A minus B, right?
Yeah.
So this is one side of it, that if you have a solution to this, then obviously GCD of M and N should divide this, right?
Yeah.
So, so only if this happens will there be a solution, right? So the other side that we want to prove is suppose GCD M and N divides A minus B, right?
Yeah.
Can we find a solution to this, right? So if you say GCD M and N divides A minus B, then you can write A minus B is equal to K times GCD M and N, right?
Oh, so we write like GCD M and N is some B.
GCD M and N can be written as some M times U plus N times V, right?
Yeah.
Where
That's
U Bézard's lemma,
yeah.
UV are integers, right?
Yeah.
So A minus B can be written as K into MU plus NV, right?
Yeah.
And this can be written as M into UK plus N into VK, right?
Yeah.
UK and VK we can call U dash and V dash, right?
Yeah.
Correct. So what we are getting is A minus B is equal to MU dash plus NV dash, right?
Yeah.
So A minus MU dash is equal to B plus NV dash, right?
Yeah.
Now let's call this is equal to this. Let's call it X, right?
Yeah.
X is equal to A minus MU dash. And if you do mod M here, right? X is congruent to A mod M, right?
Yeah.
Right?
Yeah.
And X is also equal to B plus NV dash. So X is congruent to B mod N.
Oh, so we got the answer.
So we say we got the actual answers. Like if GCD divides this, from there we have shown that there is some equality like this happening, right?
Yeah.
Where u dash v dash are integers, right? And
Yeah.
from there we can say that if we call that as x, that is our solution, and x is congruent to A mod m and x is congruent to B mod m, right?
Yeah. Oh, yeah. Let me write it down.
Yeah.
Okay.
Okay. So the next part of the proof was the second claim that said that the solution is unique modulo LCM MNN, right?
Yeah.
Correct. So suppose x1 and x2 are two solutions, right? We are going to prove uniqueness by saying that they will be congruent to each other modulo LCM, right?
Yeah.
So
So
if
just
x1 and x2 are two solutions, you
take
can just say,
take the difference.
yeah, take the difference. Is A mod M and x1 is also B mod N, and similarly x2 is also A mod M, and x2 is also B mod N. We can say that x1 minus x2 is congruent to 0 mod M, and x1 minus x2 is congruent to 0 mod N, right?
So yeah,
M divides x1
multiple of
minus x2.
LCM and N.
Correct. So that means M and N are both dividing x1 minus x2. So x1 minus x2 will definitely be a multiple, or LCM of M and N will also divide this, right? Because LCM is the lowest common multiple. This is some multiple, this means, right?
Yeah.
So LCM will divide any other multiple, right?
Yeah.
So that means x1 minus x2 is congruent to 0 mod LCM of M and N, right?
Yeah.
So x1 is congruent to x2 mod LCM of M and N. So that means that the solutions are unique mod this, right?
Yeah.
And in the special case where GCD of M and N was 1, this is Chinese remainder theorem,
Yeah.
right?
Yeah.
So that is what I had planned for this class. Now, what we need to do is one topic, which is Diophantine equations. So this is a topic that we'll probably do on Saturday.
Okay.
And after this, actually, like, obviously number theory is not over, but number theory is a much bigger subject. So there are many things that are still there to learn, but it depends on how much you want to do it, like, right? Like, because Olympiad level, I don't think it is more than anything more is required, at least for the national level Olympiads.
Oh,
Theory, what I'm talking about is with respect to theory.
yeah.
There is more stuff, that there is quadratic reciprocity, and there is order modulo primes.
Yeah, I know. I heard a lot of like the very advanced theorem.
So Hensel's lemma and stuff. There is more stuff, but maybe we should not focus on so much of number theory right now, but just learn how to apply these in problems. Like, because what we have learned so far is sufficient for your national levels. Like, nothing more than that will be required.
I just want to make sure that I can do all the
Huh.
number theory questions in my round one.
So round one, for sure, I can say that more than this will not be required by with respect of theory. So obviously, problem practice will be required for you. A lot of problems you will have to solve,
Yeah,
because knowing the theory is good, but like questions could be difficult. Like, it's not necessary that you will get it, right?
yeah.
So what we should do probably is, like, after doing this part, Diophantine equations basics, then we can move to either problem solving or different topics in your Olympiad, different topics. Like, there are geometry, there is other algebra and stuff, right?
Yeah.
So 1 second, just hold on. There is someone at the door. 1 second. Yeah. So you can think and decide like what you want to go ahead with. So for example, Saturday we'll do Diophantine equations,
Yeah.
and after that, after that, from my side, theory wise, number theory is done. So we should move on to either problem solving, or we can do other topics like algebra, geometry, whatever you feel is important for you.
Uh, okay. Actually, I can select the number theory problems from my past year papers,
Hmm.
and like I can practice.
Yeah. You can practice from there, and I can also share some books with you. Like, I think there is a nice book by Titu and Rescu. Uh, Not the book that you shared. There is another book, 104 Number Theory Problems.
Oh, yeah, I've heard of that.
104 Number Theory Problems. It has basic to advanced. Like, it is a good one, and I can send you the PDF if you want. You can
Okay.
practice from there also. There are many sources available. You can practice from wherever. But uh, your Olympiad will have other topics also, right?
Yeah,
So those topics, how is your preparation in these?
I think the topic that appear the most is algebra,
Uh,
and there are a lot of like inequalities or
uh,
some.
Correct. So you think about it, and you can decide what you want to work on. Like, you tell me a few days in advance, then I will prepare accordingly, and we can discuss those things.
And like sometimes can we do some like Q&A session?
Yeah, we can do that. Q&A as in?
Like some questions that I don't know from the papers.
Yeah. Share the questions with me.
Uh, Actually, I have some.
So
Right now I haven't started practicing.
start the practicing thing, and we can do whatever topics you feel are uncomfortable in algebra, geometry, and all. And we
Okay.
can do questions from your past year's papers and all also.
Okay.
Uh, Obviously, I cannot guarantee that I will be able to solve them. Nobody can guarantee that, but I can, if I get time, I can probably solve it. So uh,
Okay.
we can discuss it as much as I can do. So
Okay. So
uh,
like I think after this, can we do some like after the number theory part, can we do
uh,
some inequalities.
Okay, so inequalities in algebra, there is also
Like I
inequality,
some
then
some
polynomials and all equations.
and also
Um,
some like kind of some miscellaneous algebra questions that I don't know how to categorize.
okay. Yeah, we can discuss. Um, yeah, fine. We will start off with inequalities and any other type of questions we'll see. Uh, and geometry also, triangle geometry, you need to know really well.
Yeah.
Triangle geometry and some of the theorems that are there, right?
Yeah.
Have you started studying that?
Yeah, I study some. I
Okay,
know those basic things.
okay, okay. Fine. So just think about it, make a plan for what topics you need help in because we are halfway done almost, right?
Okay.
So there are 8, 9 more classes. So we need to cover as much as possible. And your exam is in when? May, right?
End of May or the start of June. I don't know.
Okay.
Because like
So we
they
have
haven't.
some time. Yeah. We have 3, 4 months to prepare. So
Yeah. And like my goal is just to enter the second round.
yeah, you will be able to enter. Just make sure that uh, don't focus on one thing so much that you ignore the other things. Like I'm
Yeah.
sure the questions will be balanced, right? It will be like some portion of number theory, some portion of algebra, some portion of geometry.
But I think there are more algebra questions.
Okay. So then whatever are your problems, just bring them to me. Like some Sunday onwards, we can start doing inequalities and things like that. Right?
Okay. Okay.
Okay.
I
Uh,
start practicing my past year papers.
yeah. Start practicing them and we can discuss those.
But sometimes like they are a little difficult for me.
Yeah, it might happen. Like they are difficult for me also sometimes. It is going to be difficult for anyone who is doing it in the beginning, right? So
Yeah.
uh, slowly with practice and all, you will get better. So don't worry about that.
Yeah.
Nobody can guarantee that they will be able to do it every question
Yeah.
because the subject is very deep and it's not easy.
Yeah.
So
But I think the round one questions aren't are not that difficult.
so then it's good only. We'll be able to solve them. So if you have any past year papers and all, then you can share with me also. I will also see how it is.
I think they are all available online.
Okay, so this is the name of it is what? Singapore
Mathematical.
Mathematical Olympiad round one.
Uh, yeah.
Mathematical Olympiad.
Just the search. I think I got a website.
AOPS website link. AOPS it is there. Okay?
No, they are not on AOPS, I think.
Oh, okay. If you have any website link, just send that link to me in chat. Right?
Wait. I
Where
think
the papers are there. No, just send it on WhatsApp to me later if you can find it.
wait. I can send to you now.
Okay. So we'll do Diophantine equations on Saturday and probably on Sunday onwards we'll start with the algebra stuff. Okay.
Yeah, I think they don't. The theory
Uh,
requirement is not very deep.
yeah, exactly. So I don't think we should spend more time doing quadratic reciprocity and all.
Yeah.
We should work on problem solving more.
Yeah.
So fine. I will see you on Saturday then. We'll finish this portion and we'll go on to algebra and all on Sunday onwards. Okay.
Yeah. Also, I think for like inequalities,
Hmm.
the only thing I need to know, I think, are just the AMGM and Cauchy.
AMGM and Cauchy should be sufficient, but sometimes it is nice to know a little more.
Yeah.
Cauchy Schwarz and AMGM should be sufficient, but it's
And
not like you have to memorize inequalities. But if you
yeah,
get the sense of how things are proved and all, like 4, 5 others also, if you know, it is good for you.
yeah, and also I need to know how to solve some simple what's that functional equation.
Yeah, that is a slightly tough topic. Functional equations is quite difficult actually. So, have you done any amount of calculus? Any bits of calculus have you done?
Like we are studying it, but like I have no foundation for that.
Like, do you know basics of functions and limits and functions limits?
I know a little.
So, like functions and types of functions, you know.
Yeah, some exponent, logarithm, like that.
Not like that, not such types. Into, onto, injective, bijective.
Oh yeah, I think bijective that's 1-to-1 and surjective.
Bijective is many one, one onto.
Yeah,
One. There are four types, right? Into, onto, one many one, right?
yeah,
So bijective is one onto, and surjective means onto, injective means one, and stuff like that. Like these terminologies, if you understand well, then functional equations is doable. Otherwise, functional equations you can't solve. It's quite difficult.
yeah,
So okay, we'll discuss all this. This comes under algebra only. So
yeah.
we will cover this, and we'll cover inequalities and all. So
So
I will look at the website link you have sent, and I'll look at the questions from there. I will also get a sense of what is required.
yeah,
Okay, I'll see you on Saturday then.
okay.
Okay, bye.